Okay, so good afternoon, everyone. Today I'm here to present my research entitled Behaviours Prevision for the Hydrogen Combustion on a CFM-56-3 Combustor. Well, this presentation will be divided into 5 parts, and I will start to make a small introduction, then to present some theoretical background. After that, I will present the methodology followed during this research, and finally I will present the results and then the conclusions. Well, in the last decades, the aviation sector has grown and reinforced its importance at an international level. According to a report found in the literature, in 2015, international aviation used approximately 160 megatons of fuel. According to some experts, when compared with 2015, by 2045, it's expected that international air traffic should increase by 3.3 times, and the fuel consumption is projected to increase by 2.2 to 3.1 times, depending on the advances in the technology and the air traffic management scenario. This creates a problem because the increased fuel consumption will inevitably lead to an increase in the pollutant emissions into the atmosphere. The combustion of fossil fuels produces emissions which are usually considered as the main responsible for the greenhouse gas emissions. For the aeronautical sector, the emissions of major concern for the climate change are usually the NOx, the CO, CO2, and the particulate matter. Well, sometimes the water vapor can also be a concern if it produces persistent contrails, which can lead to cirrus clouds. However, during this work, this research, the water vapor will not be considered as a major pollutant. For the possible solutions, if we don't consider the economic and political measures that can be taken and focus only on the technical part, to mitigate the problem with the emissions in the aviation sector, the several possible solutions can be usually grouped into 2 main options. The first one is the reduction of the fuel consumption by upgrading the technology used in the current aircrafts, always with the objective of achieving higher efficiencies of the aircrafts. And the second one, the use of alternative fuels and power sources. According to some reports, this last option seems to be the most effective. Therefore, and considering the fuels currently known, for a sustainable growth of the aviation sector, there seems to be 2 viable fuel groups. The first one, the sustainable aviation fuels, and then the use of the hydrogen, which can be used in combustion on the gas turbine engines, new engines or converted engines, and then it can also be used in fuel cells. A third solution is the use of a mix of the previous 2 options, which consist in the hybrid systems. So, the motto of this work consists in the conversion of the current gas turbine engines to the new sustainable fuels, mainly the hydrogen, which is the main objective of this research. Well, the main objective of the work presented here consists in the study of the feasibility of the use of gaseous hydrogen as a substitute of the conventional jet fuel in a CFM-56-3 combustor using a CFD approach. For that, it was necessary to analyze and compare the results obtained for hydrogen and the jet fuel obtained during the CFD analysis. This was made through the comparison of the NOx emissions produced by the jet fuel and the hydrogen for the power settings represented by the ICAO's LTO cycle for the standard operating conditions of the engine. The last objective was to analyze and compare the influence of several operating parameters in the emissions of NOx with the use of hydrogen as a fuel. The hydrogen is the simplest and most abundant of the chemical elements in the universe. On the Earth, under standard conditions, it exists as a diatomic gas, but its concentration is negligible. However, in chemically combined forms, it is the 3rd most abundant element on the planet. The main reasons why hydrogen can play a significant role in meeting the world's energy demands and addressing environmental concerns are that hydrogen meets 3 extremely important criteria. First, it provides energy security. Then, it's a promising low-carbon alternative to reduce the emissions of greenhouse gases. And third, it offers the possibility of reducing local pollutants, mainly the NOx and the particulate matter. For the conversion of the current gas turbine engines to hydrogen, in theory, to adapt the current gas turbine engines to efficiently use the hydrogen as a fuel, the minimum modifications required consist First, in the replacement of the injection system, and in second, the implementation of facilities to evaporate the hydrogen, which is usually stored in tanks in a liquid or cryogenic state. However, if we want to take the full advantage of the hydrogen's properties, also the combustion chamber must be changed. Well, in both cases, when changing to hydrogen, either the combustor outlet temperature, well, usually referred as COT, or the net thrust of the engine can be retained. Usually, when the COT is preserved, the net thrust of the engine increases, and when the net thrust of the engine is retained, the COT decreases. According to some works available in the literature, these performance improvements can be explained by the combination of two fundamental changes when using hydrogen. The first one is that there is a reduced mass flow through the engine. This one, in theory, deteriorates the performance, and then there is a changed composition in the gases expanding through the turbine. This will usually improve the performance. When we combine these two effects, the expression of the latter on the engine performance is always more relevant than the former, hence the improvement in the performance. Well, regarding the mechanisms of pollutant formation, for the conventional fuels, as we know, the pollutant emissions of most concern are usually the CO, CO2, unburned hydrocarbons, NOx, and the particulate matter. So, from an environmental point of view, hydrogen can be considered almost as a clean fuel that offers the possibility of reducing pollutant emissions, since as a fuel, its combustion only produces NOx emissions. Well, considering this research and its objective, as the NOx is the only common pollutant produced by these fuels, and considering the objectives of the work, only the NOx emissions were studied. According to ICAO, these emissions can be evaluated in two possible scenarios, which consist in, first, the NOx emissions in the full flight, or in second, the emissions produced when completing the ICAO's LTO cycle. In this case, since we only have the experimental results for the ICAO's LTO cycle, was the approach selected. The combustion model used for this study was from a CFM-56-3, which consists in an engine developed and manufactured by CFM International. In the case of the version under study, it consisted in a high bypass axial flow turbofan with a bypass ratio of 5.1 to 1, and this specific version has a dry weight of 1,966 kilograms. As we can see in this image that is presented in this slide, this engine has a dual rotor configuration with a low pressure compressor, high pressure compressor, annular combustion chamber, high pressure turbine, low pressure turbine, and the two shafts connect the low and high pressure sections respectively using a 5-bearing system. Well, from here onwards, I will describe the methodology followed to achieve the objectives initially presented. However, to simplify the explanation of the process followed, this work was divided into 3 consecutive and iterative phases. Well, the phase number 1 consisted in the correction and preparation of the geometry for the next phases, and by the end of the phase number 1, it was necessary to make the generation of an independent mesh to use in the simulations. The phase number 2 covers the entire process of defining the simulation parameters in order to obtain the correct patterns for the flow and combustion within the chamber, and also to obtain the final results for both fuels. This phase number 2 is deeply related to the phase number 1, since part of the geometry corrections were due to problems detected in this phase number 2 during the simulations. Finally, the phase number 3 consisted in the comparison and analysis of the results obtained during the phase number 2. Due to the complexity of the phase number 2, it was necessary to subdivide it into another 3 subphases. Here, the objective of the phases 2.1 and 2.2 is to credibly replicate the original operating conditions of the engine working with Jet A through an iterative process. The phase 2.3 is associated with the hydrogen simulations to evaluate the theoretical performance of the engine with this fuel. So, in this case of study, the phase 2.1 was carried out only for the 100% power configuration, and it consisted in an iterative process in which the objective was to determine the air mass flow distribution in percentage to first replicate the flow pattern inside of the combustion chamber, and then to obtain an outlet average static temperature similar to the reference values that we have from some other works. The phase 2.2 consisted in for the verification if the air mass flow distribution calculated in the phase 2.1 was the most appropriated for each power setting through the analysis of the flow pattern inside of the chamber and the NOx emissions, which we could compare with the reference values from ICAO. And the final objectives were to obtain first the final results for the control simulations with Jet A, mainly the NOx emissions, and then to find also the boundary conditions for the air inlets for each power settings. After the phase 2.2, we started the phase 2.3, which consisted in using the boundary conditions calculated in the phase 2.2, calculate the mass flow rate of hydrogen for each power setting with the formula presented in here. After that, it was necessary to run the simulations, and the final objective was to obtain the results for the simulations with hydrogen, mainly the NOx emissions and the results for the sensibility tests performed. Well, about the NOx analysis, after analyzing some articles available in the literature about studies identical to this one, it was concluded that there were two ways of analyzing the NOx emissions, and they were, first, the utilization of sub-mechanisms provided in the detailed mechanisms, and then the use of the NOx model provided in Ansys Fluent. In these studies, it was also mentioned that to simulate the combustion process inside of the chamber, the use of the detailed mechanisms allowed better results than when using the probability density models available in Ansys Fluent. So, after analyzing and test a considerable number of mechanisms available in the literature, the mechanisms chosen for this research were, first, the mechanism presented by Kundu et al. To simulate the combustion of Jet A in the phases 2.1 and 2.2, and then the mechanism of Lee et al. To simulate the combustion of hydrogen in the phase 2.3. Regarding the simulation setup, in general, the simulations carried out were 3D simulations in steady state, and the pressure-based solver was used in all of them. After some tests with the available models in Fluent, it was found that the best results were obtained for the set of models defined as shown here in the left, as we can see. However, due to the complexity of this work and the number of models applied, to obtain completely converged solutions, it was necessary to use a step-by-step approach in which simpler models were used to obtain the initial converged solutions or close to it, as you can see here for the Jet A, and then for the hydrogen simulations. We started here, step 1, step 2, 3, and 4, and finally the post-processing. And well, in here, we use the simpler models at the beginning, as we can see in here. And then after getting the initial converged solutions or close to it, the more complex models were gradually applied, as we can see here in these cases, the step 2 and 3 and 4, until get the final results that we presented on the research. Well, regarding the results, in this presentation, only the results related to the NOx emissions from a quarter of the chamber will be presented, as they were the main objective of this work. Well, starting this analysis with the emissions from the control obtained during the control simulations with Jet A, as we can see in here, this figure presents the results of the control simulations and shows the emission index at the exit of a quarter of the combustion chamber for the Jet A. Here we have the ICAO's reference data and the two approaches followed during the simulations, the utilization of the NOx mechanism and the utilization of the NOx Ansys model. Considering the two approaches used to predict the NOx emissions, presented in this figure, it's possible to conclude that for both approaches, the NOx emissions are lower at lower power settings and attain maximum values at the highest power condition. The NOx sub-mechanism clearly overpredicts the NOx quantity in relation to the reference values. However, the NOx model from Fluent can predict values for the NOx quantity close to the ones from the ICAO's database for the lower power settings. And for the higher power settings, this model also overpredicts the NOx emissions in relation to the reference values. Well, when we do a comparison between the Jet A and the hydrogen results, as we can see here in this figure, it shows the comparison between the reference values, in this case from the ICAO, and in this case I decided to use the results from the best model of the previous results for the Jet A, and the NOx emission analysis done using the two different approaches, again, the NOx Ansys model and the NOx sub-mechanism. And if we consider the models used to predict the NOx emissions, it is possible to conclude from this figure that the Ansys NOx model provides higher values than the NOx sub-mechanism for all the operating conditions. We can also see that for the lower power settings, the quantities of NOx emitted to hydrogen are nearly the double of the quantities for the Jet A. And finally, for the higher power settings, the quantities of NOx emitted continue to be nearly the double of the quantities predicted for the Jet A fuel simulations with the NOx model, and the emissions are predicted to be nearly 4 to 5 times higher than the reference data from ICAO. Well, in this work, several sensibility tests were carried out, namely the presence of the swirl effect at the swirler's inlets and the influence of the injection parameters, namely the fuel injection pressure and the temperature of the fuel. Regarding the tests associated with injection pressure, modifying these values did not cause any relevant changes in the results, and for this reason, these results will not be presented as they do not allow to analyze the influence of this parameter. Well, moving on to the analysis of the influence of the presence of the swirl effects in the swirler's inlets, here, this figure, have the results obtained for the NOx emissions associated with the quarter of the chamber, only for hydrogen for both approaches, the NOx Ansys model and the NOx sub-mechanism. And looking at this image, if we consider the same forecasting approach, this is just the Ansys NOx model values or the sub-mechanism values, it is possible to conclude that for the higher power settings, the presence of this phenomenon helps to reduce slightly the NOx emissions, and however, for the lower power settings, the values of NOx emissions remain quite close for the simulations with and without the swirl effect. To analyze the fuel temperature, to analyze the influence of the fuel temperature, the sensibility tests were carried out with hydrogen at 600 Kelvin. Well, the results for the NOx emissions are presented in this figure, which shows the NOx flow rate obtained at the exit of a quarter of the combustion chamber using, again, the same two methods, the NOx sub-mechanism and the Ansys NOx model while burning hydrogen. And from this figure, it is possible to conclude that, first, for the analysis with the fuel temperature of 600 Kelvin, the error between the two approaches used to forecast the NOx emissions is considerable for the higher power settings. We can also see that in the higher power settings, for the sub-mechanism, the NOx emissions are lower for the fuel temperature of 600 Kelvin, while for the NOx model of Ansys, the emissions keep higher than for the reference temperature. We can finally see that in the lower power settings, the quantities of NOx emitted are higher for the fuel temperature of 600 Kelvin than for the reference temperature for both approaches. Well, the conclusions of this research consisted in, first, all of the objectives were accomplished, and it was demonstrated that theoretically, the CFM-56-3 can work with hydrogen as a fuel with minor changes. Then, the results obtained to the control simulations were acceptable when compared with those of ICAO. The results obtained for the simulations with hydrogen demonstrated that with the increase of the accelerator percentage, a higher mass of NOx per mass of hydrogen is produced due to the increase in the temperature inside of the chamber, as would be expected. And finally, when comparing the NOx emissions obtained for the simulations with both fuels for the standard operating conditions of the engine, it was shown that for this geometry of combustor and injector, the quantities of NOx produced when burning hydrogen is almost twice as high as the NOx emissions for the Jet A for each power setting. This conclusion is in agreement with several other works available in the literature, which is a very good sign. Regarding the sensibility tests, it was concluded that the presence of the swirl effect helps to reduce the NOx emissions, and an exponential raise in the fuel temperature can cause malfunctions across the chamber. Finally, the fact that the changes in the fuel injection pressure have not influenced the results can be explained as a consequence of the fact that the changes in the fuel density due to the injection pressure modification were irrelevant. Well, and so this is the end of the presentation. I hope that you have enjoyed it.